All right. Welcome. Uh, Thank you to Greg for doing the last section on dilution and general ventilation. This section will start to talk about ductwork and ductwork systems. Uh, this is what we call good LEV, or local exhaust ventilation, which is a big mouthful, but this is good local LEV system design practices. You'll notice from the old drawings, these are our favorite trained lines, and you see that what's being done there is we've got air coming into a plenum, and we've got trained lines coming out. We happen to know these days that that doesn't work that way. If you want to find out how air works in a hood, you should use computational fluid dynamics, which is a good tool that we have going forward. Our objectives in this section, we will discuss the following. First thing is two important equations. These are Bernoulli's and Da Vinci's equations. So we'll talk a little bit more about that. Then we'll talk about hood design. And then I'm going to hand it over to Greg Grubb to talk about component parts and summing system losses. It will be on a different, you'll have to start it up as section 3B, and talking about multi-hood ventilation, balancing multi-hood ventilation systems. And then our velocity pressure calculation sheet, which is the easy way for you to sum all the losses and assess the static pressure or resistance in your industrial ventilation system. So let's get started. Two important equations. Thank you, Greg, for this. I just love these guys. Despicable me. Anyway, here's our local exhaust ventilation system. We've got two hoods. The two hoods are hood 1 and hood 2. And first, we'll start our fan, and our otherwise known as a motivator, or we'll call it a differential pressure generator. And it's going to get a differential pressure across it, and it will induce a draft. In this case, pulling through these two hoods, hood 1 and hood 2, protecting our worker who is using good work habits, and the air will accelerate into the hood, getting 100% of the contaminants, hopefully, if designed correctly, taking to an air cleaning device, which is B, and then into the motivator, and then to the stack, which goes to atmosphere. Let's review a little bit. We talked about pressures. Pressures are of utmost importance because pressure is how we are able to troubleshoot the system. It is the best friend of the industrial hygienist or the industrial ventilation troubleshooter. And that we talk about the total pressure, which is the algebraic sum of the static pressure and the velocity pressure. And we talked about that in the first section. These are things, the pressure we can measure in the system. And then we can sum all the losses for the hoods and all of the components. And then we can eventually choose a fan that will do what we have asked it to do and protect the worker, obtaining the proper volumetric flow rate, otherwise known as CFM or ACFM, at the hoods in such a fashion that with the work practices and how they approach their work, that it will collect 100% of the contaminants. Unfortunately, velocity is only a function of the velocity pressure. So what we must do is we must conduct pressure measurements in order to determine the velocity. We're going to teach you how to do that. All right. The first important equation. This is Bernoulli. Bernoulli was a Swiss mathematician, and he won, in today's dollars, probably $2 million from the King of France, who wanted to find out how he could determine velocity from pressure. They didn't really know what they wanted. All they knew is that they were bleeding, using blood to reduce harmful humors in people. And the fact that they were sweetening their tea with lead, which is a nice sweetening agent, draining some of their blood probably was a very effective means of reducing bad humors in people. But the problem was that it had a tendency that there was enough blood leaving the body that, in fact, we had a lot of patients that died due to the painstaking that they were doing. Bernoulli was able to determine that there was a square relationship. And if we look at our equation here, is when we get a pressure from the velocity, if we use that, it is equal to the density of the liquid times velocity divided by 4005 squared. So that is Bernoulli's formula, and we'll see it written in another format here in just a second. What we want to talk about is how do we determine the velocity and the velocity pressure? How do we do this? Well, let's talk about a duct system will carry heavy, moist dust, and air is at standing condition. What's the minimum velocity and velocity pressure in that duct? Well, we can look this up, by the way, in Chapter 5 of the manual, if you have that. The table 5-1 tells us that heavy, moist dust will move at a momentum or a velocity of 4,500 feet per minute. At 4,500 feet per minute, that carries all the dust and keeps it from falling out or salting in the ductwork, keeps the ductwork clean. And so we looked that up, and we figured out that that is the minimum design velocity for a heavy, moist dust. So if you remember from the last picture, the last slide, the velocity pressure is determined by taking the velocity divided by 4005 squared times the density factor that we'll talk about later, and we've talked about it a little bit before. And that's how we will determine the velocity pressure from the velocity, and this is something that we can measure using a pitot tube. So with our density factor being 1, that gives us, we can put into that equation 4,500 divided by 4005 squared, and what we'll find is that the velocity pressure at that is, by the way, is 1.26 inches of water column. How do I know that? Well, it turns out in my background, we use 4,500 feet per minute as a minimum duct velocity in the lead acid battery plant that I used to have. So that for lead, we were always going out, measuring with our pitot tube, and we were looking for a velocity pressure of 1.26 inches of water column, which can be read in a manometer everywhere we went. So that's a very useful number.
Hey, John, just a quick note to add in here on that last slide there with regard to using 4,500 feet a minute as a minimum duct transport velocity. One should realize that for some heavy moist dust, you may well need a velocity exceeding 4,500 feet a minute. So that's certainly the minimum, but you may need velocities that are upwards of 5,000, 6,000, 7,000 feet a minute to keep the material entrained.
Absolutely. We had a heavy viscous oil that was going into a ductwork system that they had somebody crawl in the ductwork and clean it out on a periodic basis every 6 months so that it didn't build up like atherosclerosis in a blood vessel. So they had to go in there and clean it out. They actually put somebody into and tied a rope to them and pulled them through. It was disgusting and obviously a horrible confined space and not legal probably. I can't imagine how it would be. We ended up finding out that the minimum duct velocity for this viscous liquid was about 5,500 feet a minute, and the redesign of the system included one that we designed for 6,000 feet a minute, and it kept it clean forever after that. So thank you very much for that. So here is another, we can rearrange that equation, Bernoulli's equation, and change the position of velocity pressure and solve for velocity. So in our velocity, if our velocity will be equal to determined velocity, we would take 4,005 times the square root of the velocity pressure over the density factor. And this is an equation that we'll be using oftentimes. This is typically, if you're doing any troubleshooting and you go into the field, well, like I told you, we would stick our pitot tube in position, come up with a velocity pressure of 1.26. And at standard temperature, we would put the 1.26, take the square root of that divided by 1, which is 1.26, the square root of that times 4,005, and that equals a velocity of 4,500 feet a minute, which is what we knew we had wanted. This is a very difficult thing for people to understand, and I don't. It's easy as for Greg and I, because we've been doing this for many years, and it's something that we take intrinsically obvious. But this relationship between velocity pressure, velocity, static pressure, and total pressure can be confusing. So I like to break it down into simplistic functions. In this case, you could take a manometer, a U-tube manometer, and if you face the manometer in the pointing towards the wind coming at it, into the wind direction, what you will get is a velocity pressure. If you take that velocity pressure and take the square root of it times 4,005, because this would be some standard amount, you could come up with the velocity in feet per minute. And for example, let's say you come up with a velocity of 5,280 feet per minute. 5,280 feet per minute, that is a mile every minute, or about 60 miles an hour. So you can change this back into almost any common, something that would have a great deal of meaning to you. But you could actually do this by taking a velocity pressure measurement using a U-tube manometer. And so what does DF represent? The DF is the density factor, and that is the ratio. I'll change that from ration. The ratio of the density of an airstream at actual conditions compared to that of standard conditions. So we have the density factor in that second, right down here in this second equation. Density factor is equal to rho actual, which is the density of air at actual conditions divided by in a ratio to standard conditions. So we always take our actual, what we're reading, compared to 0.075 pounds per cubic foot, which is what the weight of air is, if you remember from section 1. The density factor is made up of 4 individual components. This is all of them. They're very important. And if you think about it, it's going to be intrinsically obvious. In elevation, we talked about that in section 1. As the higher we get, the less dense the air is. The air is only 35% dense at the top of Mount Everest that it is at sea level. At low pressures, that's not really the pressures of barometric pressure. We're talking about pressures that compare to the atmospheric pressure at standard conditions. And typically about 20 inches of water column. We'll talk about that later. Temperature, we're going to be talking about that a lot. 30 degrees Fahrenheit gives us about something that we want to consider. Moisture, when moisture is really a misnomer there. What we want to say is air really air? Well, air is always air, but it always has some degree of moisture to it. But if you're ever conveying with something like argon or another non-explosive, like something like nitrogen, if we're using pure nitrogen gas, that has a different density than would air. And of course, air has a different density when you put a bunch of moisture in it. So especially at high heat conditions, on dryers, we're always considering the moisture. So our true density is that again, rho actual, down here in this last one, is rho actual divided by rho at standard, which is 0.075 pounds mass per cubic foot. And that is equal to the density factor for E, elevation, density factor for P, pressure, times the density factor for T, temperature, times the density factor for moisture or any other contaminant that's inside that makes a constituent part where it doesn't become like air. And look at this. This is the product of each of these. It's all four of these multiplied together. Very important. All right. So velocity, a velocity pressure of 1.25 inches water gauge was measured in the duct. Remember, 1.26 was 4,500 feet per minute. What is the velocity V at that point? And the density factor is 1.0. Well, we can take that velocity. We know it's going to be about 4,500 feet per minute. So we take our 4,005 times our velocity pressure divided by the density factor. Down here, we're going to use 1.25 divided by 1 and take the square root of that in this fashion right here. And what do we come up with? 4478, approaching 4,500. We knew that. In the case, what happens when we're at a density factor of 0.5? By the way, that's not that uncommon. That is a temperature of approximately 600 degrees Fahrenheit will get you a density factor of 0.5. So what happens? So when you're reading a density, you're reading a velocity pressure of 1.25, which down here we're going to get that same velocity pressure, but we're going to divide by 0.5 before we take the square root of it. So it's 1.25 divided by 0.5, take the square root of that times 4,005. That's 6,332 feet per minute. So what's happening to you is when you take at a high temperature or a non-standard density, the pitot tube and the manometer will lie to you. It's going to tell you a falsehood. So it is very important that when you take measurements at elevation, at temperature, at moisture, or at low pressure, that you consider using the velocity pressure Bernoulli's equation before you start writing answers down. You need to make the calculations. Okay. A velocity pressure VP reading was taken in the duct, measured 1.25. What's the velocity at that point in the duct? We already done that. Well, how do we do it? We go to this velocity traverse data form, which is located in the back of the Industrial Ventilation Manual in section Appendix C in Chapter 14. Notice here what we have is we have a technician name, the date, where you're taking it, calibration, and the type of device, and then this is a very important section right here. It's right here, the density factor. But we're going to come in there, we're going to take our reading at 1.25, and we're going to come in there, and we've got to consider that density factor in elevation. So we're going to, let's say here, 70 degrees. We're going to look at 4,000 feet. Well, 4,000 feet above sea level, so we have the proper normal standard temperature, but we're at 4,000 feet. At 4,000 feet, we're at only 87% of the molecules that we would have at sea level. So we have to take that into consideration. Or we can change it to change the temperature, so that here you go. We're at 0 feet above sea level. So we're at sea level, and we're at 200 degrees. Well, 200 degrees, the molecules spread out in that fashion, so that we're only at 80% of the density that we thought we were going to be when we take a pitot tube reading. So we have to understand this before we can do measurements. And here's there's our elevation factor. Our density factor was 0.8. And then what was our static pressure? We were measuring at a place that was atmospheric. What about our temperature? Temperature was at 200 degrees. We're going to be at a 0.8 density factor for that. What about moisture, intrinsic moisture? No, we didn't say there was anything with the moisture. So now what we end with is a density factor that is the combination of temperature and elevation. That's 0.7. The air will only be 70% as dense as it is at standard conditions. And the pitot tube lied to you. So we can go into this in chapter 9, table 9.7. This is a wonderful, you can tabulate this if you can, put a little into your manual on that page, and you can come down with a combination of 4,000 feet above sea level and 200 degrees F. We come across here to 4,000, come down, look, it's 0.7, doesn't lie. So now we see that we've got both on our velocity traverse form, we've got our 0.87, our 0.80. So our total is 0.70 for our total density factor. So when we take our when we get our reading of 1.25 here, we will use that and divide by 0.7 and take the square root of that, and what that will end up is giving us a real velocity of 5,352 feet per minute. And that, of course, will change our CFM when we get to the bottom to come up with a volumetric flow rate once we take a lot of measurements. Okay, so remember that our density factor is the density factor for temperature, 0.8, times elevation. That gives us the combined total is 0.70, and that's what we use in our equation. And then we take that exactly, that same formula, and we come up with that 5,352 feet per minute actual, not the 4,478 feet per minute that we immediately thought it would be at standard conditions. So it's lying to you, it's underestimating due to density factors. That's what's going to happen. And velocity leads to the second important equation. Leonardo da Vinci was standing out one day and he noticed water running in a brook. And he said, I can go out there and I'll put a V notch in it. I can figure out how much water is running through the V notch by the height of the water in the V notch. That gave him an area of displaced area that the water was taking up. He then put a straw in the fluid in the little stream and got a velocity for that, and found out that the volumetric flow rate, Q, and that's what we're going to call it from now on, Q is equal to the velocity through that duct times the area of the duct. That gives us a volumetric flow rate. It is not a volume. It says volume here because that's what everybody calls it. It is a volume over time. So it's a volumetric flow rate. And I don't care if you use volume because that's what people talk about. But as long as you understand that it is a flow rate, it's a volumetric flow over time, cubic feet per minute. And if you think about it, feet per minute times feet is feet times feet times feet per minute, also known as cubic feet per minute. That allows us to keep that straight. All right, area in square feet. It can be determined by mathematics. In the case of a square duct or rectangular, we can do height times width. That gives us our area in square feet. As long as the height is in feet and the width is in feet. If it's in inches, then you're going to get 144 square inches per square foot. You can play that game. Everybody's done that before. For round duct, we can use the cheater method, which is my favorite method, which is we take our diameter in inches, we square it, and we multiply times the area of a 1-inch circle. This 0.005454 is the area of a 1-inch circle, and the ratio of areas of circles goes up at the square of their diameter. So know that D is in inches. It's an easy way, great way to save some time if you do this for a living. So a 42-inch diameter duct carries 3,500 feet per minute in it. So a velocity of about 40 miles an hour, by the way. What is the volumetric flow rate of air traveling through that duct? Well, we need to determine Q, V, and A, but it's asking us for Q. Is it giving us V and A? Well, it's given us V, that's 3,500. Area of a 42-inch duct, that's probably what we want to solve first so that we can come up with Q. So our diameter of 42 inches, 42-inch duct is A. If you take 42 times 42 times 0.005454, or do it the pi r squared method, you find out that the area of a 42-inch duct is a little bit more than 9.5 square feet. So when we use that in the formula, and we go back to Mr. Da Vinci, Leonardo, and so we take our velocity in feet per minute times the area in square feet. What we come up with is 33,674 CFM. Is that ACFM or SCFM? That's going to be a good question. We'll talk about that here in a minute. But let's just tell you that if you're measuring it, if we're doing this theoretically, we could theoretically say SCFM if we said it was all at standard conditions. But other than that, if it represents anything real, it's ACFM. So anything real in the world is going to be ACFM. Unless we're doing unless we're doing something that will that we want to talk about standard conditions, or if we're counting molecules. We'll talk about counting molecules a little later. All right, here's our second important equation. The algebraic rearrangement. What we can do, Q is equal to VA. If I divide both sides by V, I come up with A is equal to Q over V, and V is equal to Q over A. So if we take this is a great little handy thing, and I want you to at home to write down this circle, put Q in the top, put a T in the middle, and V and A in the bottom. So when you want to determine Q, you put your hand right here over the Q, block it, and that gives you V times A. You would read it right across here, V times A. If you want to determine A, put your hand over A, that's Q over V. Or if you want to determine V, you can use Q over A. It's a great little high school cheater, another cheater method, but it's very handy. Just if you don't forget, or if you don't remember, you can always go back to that. So let's talk about it. This is a spraying station, also known as a paint spray booth. A spraying station is designed with a volumetric flow rate of 8,400 ACFM. Okay, notice that's ACFM. The front of the booth is 8 foot high by 4 foot 6 inches wide. What is the face velocity of that hood? And how would you determine that? Well, we'll talk about that in a little bit. The actual face velocity is later measured at 35 feet per minute. What's the volumetric flow rate now? Well, the spray station, if we take it's designed for 8,400 CFM, we can take that, divide that by our to come up with V, we're going to take Q divided by A. So Q is 8,400. Area would be 8 times 4.5 feet. We got to keep those units. It's not 4.6 feet. It's 4.5 feet. That gives us a velocity designed for at 233 feet per minute. We're only getting 35. What is obviously our CFM is significantly lower, our ACFM. So the actual face velocity is later measured using probably hot wire anemometry, or hot wire anemometry. What is the volumetric flow rate now? Well, remember Q is equal to VA. So what we've got is our V is 35 feet per minute down here, times our 8 feet by 4.5 feet. And what happens is we get 1,260 actual cubic feet per minute, way less than it was designed for. Using a face velocity. Now, this is a client is required to meet the U.S. EPA method 204 as part of the conditions of their permit. This means that there must be an average face velocity of 200 feet per minute through all openings anywhere, and in this case, in each hood. At startup, one hood's 24-inch connection had a duct velocity of 3,700 feet per minute. The plant is at sea level, and the temperature was 90 degrees. So it's we are at sea level, but we're at 90 degrees. Now, The front opening is 4 feet by 13 and 3/4 feet. Did this hood meet the permit requirements? We can determine this, and this is what EPA would do in coming back to do it. And they would make sure that it was. So we take our Q is equal to our velocity times the area of a 24-inch duct. That's 3,700 times by the way, look at that number of the area of a 24-inch duct. The nice thing to know, 3.14. It's actually 15927, and it goes on for way more than we want to talk about. If you recognize that number as pi, you're correct. So the 2-foot duct has pi square feet. So our velocity times our area equals a total CFM. And this often happens that we have to come up with our total CFM before we can back into our velocity. But total CFM in this case, 11,625 ACFM. We then come back and solve for velocity by taking our volumetric flow rate divided by our area, and we find that in fact it did exceed the 200 feet per minute minimum requirement for method 204, which by the way is found in chapter 13 of our ventilation manual if you want to look at that too, or the 40 CFR part 60 in the Federal Code of Federal Regulations. All right, let's talk a little bit about hood design. Hood design is my favorite part. Other than the fans, it's my second favorite part. In this case, we've got a fella here that's grinding, and this wheel is slinging the dust up. We notice that it's fortunately this high-speed buffer polisher is only throwing the dust up at his apron top. It's not there's no way possible that can reach his breathing zone. I'm not buying that. Here's our local exhaust ventilation system. Let's get it started. Somebody bump that fan. Okay, we bumped the fan. We're talking about the hoods. These hoods are the interface between the human being and the engineering control. The engineering control is the system that protects the human being. This is where most of our engineers have the most trouble because they don't spend the time to understand the relationship between the human being and the engineering control. This is where it's happening. It's happening right here. So engineers watching this, industrial engineers are much more apt to understand some of the principles of industrial hygiene. So if you're a mechanical engineer, if we give you the cue to start up your system design, you will always get a good system. If you don't understand the principles of capture and the effect of protecting this worker with his work practices, then it is highly unlikely that you will not meet the contaminant requirement at the end of the system when it's been installed. In this case, we have an employee who, when he takes his notebook and goes over and looks very closely at this degreasing tank, is going to find out that he's going to get a face full of degreaser, and whatever that contaminant is, that's not a good thing. So canopy hoods are not our favorite hood. Sometimes they, especially with hot processes, we have to use them, but we're very careful about that. We like, as industrial hygienists and industrial engineers, we like to take the contaminant away from the breathing zone. As a matter of fact, we like to go down in a way whenever we can. And this would be this may be another vapor tank here. We have two hoods. We have our air cleaning device. We have our motivator and our stack that takes it to ambient atmosphere. Hoods are the single most important factor in establishing a system's volume. And you see, I wrote this, and it's the system's volumetric flow rate. But we talk about it all the time in volume. But that also will, the volumetric flow rate will dictate the size and the amount of energy requirement that it's going to use. And it will also, the volumetric flow rate, because gazintas equals gazoutas, will establish how much air will be needed to replace the air that you're taking away. This is a picture in a foundry that I did some work at years ago, and this is a shot peen booth. It's very well contained. When the dust collector system is not operational, it doesn't do a very good job, even though it's almost 100% contained. When it turn on the dust collector, there you go, before and after. It just works that well. But how do we come up with a CFM and the volumetric flow rate? That's a little bit of a different. We'll explain that to you as we go along. Before and after. First step, establish Q. We've got to come up with a volumetric flow rate. Anybody can remove a huge amount of air and remove the pollutant. That was in what Greg just talked about in the last module on dilution ventilation. That requires huge amounts of air in order to get the contaminant out. So anybody can do it in that fashion. But it requires very big control equipment if you're going to get out the contaminant. It also requires big replacement air cost and big fans with big motors. The solution may be a local exhaust hood. If we can capture the contaminant at the point of generation, that's where we can do it with the least amount of air and the most effectiveness. If you want to brand a bunch of cows and they're coming out of the barn, where do you want to catch them? Do you want to catch them as they come through out of the opening, or do you want to wait and let them go out and graze a while and then have to go get them? It's the same kind of concept. If you can capture the contaminant as it's being generated, close to the point of generation, it's very easy to do it with a very small amount of local exhaust. Your challenge: to remove the smallest amount of air with the greatest concentration of pollutant, because it will make you, if you can do that, it will require a small control system. Dust collector systems are based on their Q. The bigger the Q, the bigger the dust collector. When you can have a smaller amount of CFM, you can put in a very small dust collector. It does matter how much dust is in it, but not nearly as much as the amount of air that it has to control. Also, the smallest amount of replacement air. That allows you, certainly, the BTUs that you have to add back to it, you may want, if you can recirculate it, that may be a very important thing to do. And that's going to be a very small fans with very small motors. This is where your company can be more competitive than your competitors in our country or in other countries, wherever they are. If you can do it with less air, that's what's going to save your company money. It starts at the hood. Look how close we've brought this. This is a capture hood. This is not an enclosing hood. This is what we call a receiving hood. We are propelling the dust off of this wood directly into the hood. And it is very important that you get very close to the point of generation. This hood, as shown, is 6 inches from the tool, and it requires 440 ACFM. Can you capture 100% of the contaminant at further away? No problem. Well, let's move the hood back to 12 inches from the tool. That's twice the distance. Look at what happened to the ACFM requirement. 4 times. At twice the distance, it requires 4 times the air to capture the contaminant. This is trouble. Now you have just gotten in a position where your company is buying a bigger dust collector than everybody else that's doing this, whoever knew the principles of air, and you're not saving your company money. This is in Rutherfordton, North Carolina. This is a brass foundry, and this is a furnace hood. In order to, you take the scraps after you pour the brass, and you end up with stems and a lot of pieces of flashing of brass that you want to return to the brass ladle. So what they want is an open top. So they have to have an open top in order to put the scrap back into it. So you've got to have it open. how close do we want to get to this hood so that we can capture 100% of the brass. The brass fumes are coming off. You can see the brass fumes coming off there where the arrow is pointing. And brass is not a terribly toxic contaminant. But you know what else comes off? Some more volatile contaminants that are intrinsic to all brass. One of them is arsenic. One of them is lead. So what we want to do is we want to make sure, because these fumes are going to be laden with other contaminants, antimony and the like. And so we definitely want to capture them as close to the point of generation as possible. Note that we have a slotted hood that is, you can see the slot there, you can see the slot here. And so our hood inlet is located as close to the source as humanly possible. This hood sees a lot of abuse. Look what it's made out of. It's made out of steel. Well, the heck with steel. Look, it's made out of, looks like 5/8 inch steel. That's not steel. That's mama steel. That is very thick steel. And so it's going to be, note also that it's got a couple things here. It's got some lifting lugs so that you can lift it off when they need to clean it. And it's got access that allows you to get inside and clean this out. Hood types. We have a simple hood and we have compound hoods. These are two different kinds of hoods. The compound hood is one that you just saw that had a slot in it. The compound hood has a slot loss and a point of acceleration where air is coming from standstill up to full velocity of the slot. It then has an area where the velocity slows down and allows static pressure to accumulate inside here. This is called a plenum. A plenum is a box that holds equal pressure. And then we have a transition where the air comes up to a full velocity in the ductwork. Our open face of the hood is right here. In this case, the open face of the hood is what we would think. It is just an open-faced hood. And this can be a paint spray booth. This can be that slot, that hood that we saw that was a receiver hood. It also has a transition loss. We look at the aerodynamic losses. Aerodynamic losses are something we'll talk about in a minute. In this case, the aerodynamic loss is the same here and here, but it's different at the face and it's different at the slot. So compound hood, two places of acceleration, one here, one here. In the simple, we really don't have an acceleration point here because the velocity here is slow enough that I don't care. And we'll talk about that a little bit later. And then here we come up to full duct velocity, which will be in excess of approximately 30 miles an hour or about 3,000 feet per minute. So a simple hood is a hood with a face velocity less than 1,000 feet per minute. What's the face velocity in a paint spray booth, for example? About 100 feet a minute. And that's different in different places. How about a laboratory exhaust hood? That's going to be about 200 feet per minute. So a laboratory exhaust hood is not a slotted hood necessarily. It is typically thought of as a simple hood because we have one point of acceleration, because the velocity the loss here at less than 1,000 feet per minute is so small that it is insignificant to the loss compared to the transition where it accelerates to full velocity. And if you look at that 1,000 feet per minute, the velocity pressure, it would be, back to our Bernoulli's equation, is 1,000 divided by 4,005 squared. So that's about 1,000 divided by 4,000 is about 0.25. 0.25 times 0.25 is 0.125. It's very, very small. So below 1,000 feet per minute, we don't even have to consider it. Let's look at this enclosing hood. They can be either simple or compound. In this case, this is a combination. Our velocity here looks like a slotted hood, but it's really not a slotted hood there. But it is a slotted hood back here. Look at our slots. We'll talk about slots and compound hoods a little bit later. But let's talk about this first. This is a box. We watched because my industrial engineer and I sat there and watched the people. This was what they do is they take toner cartridges and they take this compressed air line, small air compressed air line, they stick it in the toner that's being recycled, the toner cartridge, and they use compressed air to blow it out. What happens? A bunch of black stuff comes flying out in their face. So what we were able to do is we constructed a hood made out of cardboard. We put a small fan on the backside of it, and we found out that by sticking their hands inside here with the compressed air gun, that they could put it in there, face the slot of the cartridge slot towards the backside, and when they made a ton of smoke or dust come out, it was all projected up in this direction. This is an area where they can view, so they can see there is a light inside, so that they can watch and see what they're doing. And what we know is that this is a hood that completely or partially encloses the process or contaminant source. These are always the best sources, best control devices in the control hood designs. They are so good that the most successful hood of all times is designed this way, and that would be a paint spray booth. There are millions of them probably around the world. They protect people from exposure to toluene diisocyanate found in a paint spray called DuPont Imron paint, and they do it very effectively. With it has an allowable, the TLV of as I remember on TDI is 0.1 or 0.02 parts per million. We're talking about something that is highly toxic. And when was the last time you heard somebody succumbing to TDI in a paint spray booth? Laboratory exhaust hood. That is probably the second most successful hood of all time. And then a grinding hood, which is also probably the third most frequently found hood available anywhere. So when you enclose your process, and this is something we say in toxic materials, we say that you should never use an exterior hood or a capture hood with a toxic unless you have to, because when you can completely enclose the contaminant, you will be successful every time. Let's look at the simplicity of this. Our opening here is about I'm going to say that's, I think, 8 inches by 2 feet, about 1.5 square feet. We did an inlet in-draft velocity of about 200 feet per minute. That 200 times 1.5 is 300 CFM. 350 CFM is 4,000 feet per minute in the duct. If it's a 4-inch duct, that is a 4-inch duct. We can pull 350 CFM. We will pull 200 feet per minute through that face. We will get 100% of the contaminant, and now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of these machines is 3,500 CFM. A small 16 cartridge collector was used, and it was very successful. Look, this is a year into it. Find me some black dust. Tony's cartridge dust is black, and there you can see it on the back. It's very successful. Enclosing hoods, another one. This is a fertilizer screening. This is not out of focus. This is not, the vibration is happening because this thing is vibrating like crazy. Don't lean up against it. It'll take your hide off. But this is what we use. We're going to acquaint you here in the most significantly used part of the Industrial Ventilation Manual of Recommended Practices since its inception in 1950, approximately. Where are the VS plates found in the final chapter, or in chapter 13 of the Industrial Ventilation Manual. That said, these are known, submitted, and peer-reviewed schematics that tell us how properly it has been done many times before, and it gives away all of the secrets. Look at here, Q equals 200 ACFM per square foot through hood openings, but not less than 50 ACFM per square foot of screen area. No increase for multiple decks. Minimum duct velocity. Look at all that information. This is all the things you wanted to know. And that's for a flat deck screen, which is what this one is. Also used for cylindrical screens. There are 155 of these in the back of the manual, and they tell us everything from soup to nuts, from kitchen dishwashers emissions to paint spray booths. There are 4 or 5 pages of paint spray booths, to welding. There's 4 or 5 different ones of those, to laboratory exhaust hoods. It's the most useful part. And we oftentimes told it's the most useful part of our industrial ventilation manual. Exterior hoods. When do you use them? Well, these are hoods that are located near an emission source without enclosing it. So we would like to enclose it. Here is what's happening here is we have a very high temperature, high pressure extrusion hood, and it is extruding molten plastic. What comes off of molten plastic is distillate fractions of polymers. Oftentimes they're going to be everything from aldehydes, ketones, to long chain aliphatics such as paraffins and the like. It's not something you don't want to be breathing, that kind of stuff getting down in your and condensing and getting those fumes getting into your lungs. So we take them. They're sticky, gooey, they're nasty, and we have a hood that is located close to them. Why are we not enclosed? Let's enclose this hood completely. How does the employee get this? Is constantly being, was part of, again, watching the employee do their job and watching them look at they're constantly into these melting spaghetti strands that are going into a water bath. This is on wheels, this tray of water. This is moved constantly. They will not use it if you put a hood on it. They will rip it off. And we learned the hard way. So this is how that's used. Here's another type, canopy, exterior hood. This is another type. This is an exterior hood that is located above the source. And in this case, it is oftentimes we only really recommend it for high heat sources, because that is now it becomes a receiver hood, in that the hot molten fumes are being projected upwards into this. This is actually one that I did back in my lead days. Notice how I didn't get this should have been a very short piece of flex hose, which Greg is going to talk about later, about the losses that are significantly more, not to mention the extra elbow here and the extra elbow there. Well, look here, what we did right. One thing that we did right was we put this molten lead pot very close to the molten lead, or the canopy hood very close to the molten lead pot. Imagine trying to stick your head inside that. It's not going to happen. How could I have done it better? I think we could have put some sheet metal that would have hung here, or some non-flammable curtains that maybe went down across here, and maybe we could have gotten 2 sides enclosed. 2 sides enclosed is great. 3 sides enclosed is also known as a booth. If we can get a booth, we already said how great that was. So that's what we should have done. This is actually a VS plate. This is a slotted hood. They can move the barrel in and out. This was originally designed with a normal 22-inch 55-gallon drum, but they changed to this. It's not quite as good, but it still is. Notice it's enclosed in a booth. This is a weigh scale, so they're doing a weigh up constantly into a bag from a bulk container, and we have slotted hoods across the back. And that's what we use. This is how we're using the slots for distribution. It's only to get the air to distribute this way, because notice all of our air is being taken away at a location that is at the centroid of the distribution plenum. The slots are used so that we have the velocity, same velocity here as we have here. Same velocity right in the center as we have out here. And that's done by having a very large plenum behind back here. So what we say is our slot velocity must be in excess of twice the velocity in the plenum behind it. So our V slot is greater than 1,000 feet per minute, but it must be less than 1,000 feet per minute. So it should be greater. It must be twice the velocity of the plenum itself, and it should always be greater than 1,000 feet per minute. Let's talk about them a little bit more. Slots are, or otherwise known as compound hoods. Slots are used for proper distribution of air across a large area of contaminant dispersion. Here's a common misnomer. Everybody thinks this is true. An increased slot velocity does not increase the hood's effectiveness. Now, I would say that if you increase the slot velocity by simultaneously increasing the volumetric flow rate, then yes. If you increase the flow rate, absolutely. But increasing the slot, having a higher slot velocity does not increase the hood's effectiveness one iota. That is a myth busted. Don't do it. You should call me if you ever want to design a slot that is greater than 2,000 feet per minute, because it probably is not working. It's going to work against you. All right, here is our exterior slotted hood. This is from my old factory. This is another means of distribution. We're not using the resistance across the slot to get even distribution. We're using the fact of this called a fishtail. This is a fishtail slot and a fishtail hood. And note that the resistance of the air has two particular directions. It can either come from here all the way up to the top, direct path right from the middle, or it can go this extra little bit. It's going to go from here all the way up. Well, which is longer? Well, obviously this is a hypotenuse. So this is a little bit less resistance, but only a little bit. And in testing these, we'll have in excess of 90% of the velocity here, as we do with the shortest path. So we're still getting very effective capture even out here away from it as we are towards the middle, somewhat weighted towards the middle. That's a fishtail. Distribution. It's all about distribution, because we're wanting this employee to be able to work and do his work anywhere across that entire face of that slot. Here's another one. Notice these are slotted hoods. Their slots are, you can see them, they're facing downward. These are fishtail slots in a manifold, by the way, that you can't see. This is sulfuric acid being poured into a pug mill, which is nothing more than a paddle mill. There are paddles that are rotating down in this area, and all the sulfuric acid is by the way, 50% sulfuric acid being poured in, obviously a stainless steel tank. This is for the digestion of leather before it to be made into gloves, or made into fertilizer, I'm sorry. And at the other end, the skins were made into gloves on the factory next door, by the way. But this is a pug mill. Again, distribution. And there's even one more distribution down there. There's that hood down in that end. So let's look at this. We're going to see if we can get this to work on a webinar. You might want to turn up your, and I'll talk over it so that you'll even understand a little bit more. All right. All right, here we go. There's a paint spray booth. Notice the projection is causing a backflow. And of course, he's not wearing a respirator that's activated charcoal either. So notice on this one, here they are, they're grinding and they're throwing the contaminants, particulate contaminants outside the hood. Here is one that projected directly into the hood. Now we're getting virtually 100% capture. Here we are, the hood is towards the right. And again, this is projecting the particulate into the room where it has to be used. Dilution ventilation is being used. This is the only way to get rid of it. Once it's in the room, it's just going to be dilution ventilation and general exhaust fans. By the way, that's about 100 CFM fan. It may be 200. Now, local exhaust ventilation, here we go. We've got, we're projecting directly in, that's a receiver hood, working very effectively on this pump sander. Here is a planer. We have direct, that's a local exhaust. It goes through a ductwork system all the way out to an induced draft fan that is now pushing through a final contaminant control device, a cyclone. And that goes to atmosphere. Again, projected in the wrong direction, not doing anything for the contaminant control. That is psychological contaminant control right there. This is what we really wanted to show you. We're going to be feeding some limestone dust into this. We've got a partial enclosure using this enclosed hood, and we're going to be pouring limestone down, and we'll generate a cloud of dust. This is our damper that we can use to control the contaminant, and we have a pitot tube. You can see the pitot tube in position. We're going to set this up. We're going to feed in our limestone dust onto this plate, generating a major amount of CFM, of contaminated air. We're in this hood, enclosed hood, we are 100% captured. Well, we're going to adjust it to where it is 100% captured. We'll open up a little, there we go. Now we've got 100% capture. By the way, smoke is a very wonderful way to use it. And that was 400 CFM is getting 100% of that contaminant. Now let's remove the face and open up the face a little bit more. Well, not nearly so good. We're now you're projecting. Unfortunately, we can't help it. We're projecting some limestone dust out, and now a human body, even a human body moving at 200 feet a minute, will cause some of the dust to come out and infect and affect the employee. Let's watch it here. It's projected out. Let's see if we don't get an employee to walk by here at a very slow pace and see if he doesn't generate. There you go. There you can see the contaminant is out beyond the reach of the hood. Now we're going to remove the face of it, and now we have a flange to it. This is an exterior hood. Now, you think we can catch 100% of it material? Well, I don't know. We have to ramp it up with a lot more air. We can do it. Now watch the air come. There you go. We've had to come up to 1270 CFM from 400. Now, what I want you to see here, look at all the dust that goes behind the hood. Watch what happens to the dust that's close behind the hood. It's as effectively captured as the dust out in front of the hood. Because what we're doing is we're allowing suction to happen in space, and it's when you suck in air, you're getting the dust that's behind your ear as effectively as the dust that is out in front of your nose. So it doesn't understand. Static pressure degrades, remember, in all directions, and so air will come from behind, as well as you cannot project suction in a direction. And if you don't believe this, do this experiment at home. Put a candle on the table in front of you. Blow it out at length. Light it again and try to suck it out. Try to suck out your birthday candles. It sounds funny, but you cannot suck out a candle. You'll burn your lips before you can suck out a candle. So let's use a face velocity and slot velocities. A slot length on the hood picture to the right is 36 inches wide. The slot velocity is to be 2,000 feet per minute. What is the width of the slot if the total flow is 1,500 ACFM? Well, we're going to use Q is equal to VA. That's how you would do that. And of course, what we have is our slot is going to, our velocity we want is 2,000 feet per minute, but we're going to take our length of our slot times our width of our slot to come up with our area of our slot. So what we get is we do our equation. of V times that, and we come up with to determine the width. The width ends up being 0.25 feet, which is 3 inches. So we've just designed, effectively, we have designed that hood. All right, let's talk a little bit about that, where that employee is and how that exposure and that enclosure interface. Let's look at this. Better enclosed is better captured. Look at that. No doubt about it. It will take 1/10 of the air in this hood that it would take in this one because of so much less air, because air is the suction will degrade you'll be bringing air from behind the hood. What you would like to do is put it in the enclosure. The generation will probably be here. The displacement, and we have a VS plate that tells us how much air is displaced coming out. Better enclosed is better captured. Direction of airflow, we want it down and away. We don't want it up through the breathing zone. This will have a tendency to again, unless we have a hot process that's coming up, what's going to happen is we're just going to have a major exposure of this employee in this position. Let's talk about the pressures. This is a diagnostic tool that we're going to use time and time again. Very important. So let's talk about it. The hood static pressure. Memorize this right now. That's our static pressure sub H. So SP sub H is the hood static pressure. What we're describing is this is a measurable amount of static pressure that you can, if you come 2 duct diameters behind the hood face, long enough for the air to straighten out and not become less turbulent, we can measure using a manometer, and it's the static pressure directly behind the hood. There are 4 components that contribute to that. All right. Number 1 would be the slot loss. Well, we've already told you that the slot is only half of the hoods that we will design, and that's only in the case where you have a compound hood. So as a simple hood, we won't even take that into effect. But let's talk about it because it is one of the things that we would think about. We would use a factor, our slot loss factor, which is the same for all slots, and times the velocity pressure at that slot. These factors are all a function of the velocity pressure. The velocity pressure, which we've learned how to calculate that. So number 1, let's just do this, and they'll be in red. That's our slot or orifice loss. It's Fs times Vp sub S. All right. Here is the one that we used on the simple hood. This is the hood entry to duct loss. It is F sub H times the velocity pressure of the duct. This is the F for the factor for the hood times the velocity pressure going in the duct. That will always be the same thing. All right. Now, acceleration loss. I wish we didn't have to say this, but it is typically it is one of, if not the most largest amount of resistance that we find, or energy requirement that we find for air that enters a duct system. What we have to do is we have to get this 0.075 pounds per cubic foot, this air that's at a dead stop in front of the employee, we have to accelerate it from a dead stop, and it weighs it weighs 3/4 of a tenth of a pound. That said, we've got to have enough energy to suck that air in from a dead stop. So this acceleration loss it's there every time, and oftentimes it is the majority of the energy that's required, especially in highly efficient hoods. The other losses we can forget about, but I don't want you to forget about them. We can forget about them once I tell you. Other losses, they're fittings or filters. If you've got something else in your slot, whether it's expanded metal or a filter that you put over top of it, or something else in that fashion, you have to take that, obviously have to take that in consideration. So if we throw that out the other loss, we only have 3. If we're talking about a simple hood, we only have 2 and 3. We don't even need the slot. But you need to be able to think about the slot loss, the hood entry deduct loss, the acceleration loss, and the other losses. And we call them losses because they are energy requirements that have to be overcome. So that's why we call these things loss. So it's good to think about them as a loss in energy that must be made up. So we can also call it an energy consequence. So it's consequential. So we've got a formula now that we can put in there. So our static pressure of our hood, and we can do this. The math is really easy if you'll think about it. It's a big equation. Don't get lost. Remember our red one above? That's our slot or orifice loss, and that's a factor of the slot times the velocity pressure in that slot, plus the factor for the hood times the velocity pressure at the duct, because that hood will enter the duct. And so you're always talking about, we use it in reference, the aerodynamic losses in reference to the velocity that they have to come up to in the duct. And by the way, the 1 VP is also a 1 VP of either the slot or the duct. So that will be used plus our other losses. Now, look at that. That is an entire equation. Look what we did. We put it in brackets, and we have a negative sign in front of it. Why is it negative? Well, because this is going to be on the negative side of the fan, and it's going to be suction compared to where we will refer to, which is the atmospheric pressure. So it's negative compared to atmospheric pressure. Now we're going to write it just a different way, but it's going to be the same. It's going to say the same thing. Do not let me scare you with this. Here it is. We'll call it the absolute value of the static pressure of the hood. Now we cannot call it negative. So we can think of it as losses in a positive fashion, as energy losses that must be added to the system, or it won't pull the proper velocity pressure or the proper Q, and it will not protect the employee. So we must have a certain amount of suction, which is what the static pressure of our hood is, a negative static pressure. We can call it vacuum. You can call it suction if you want. I'm going to call it negative static pressure of our hood. But what it is the static pressure or energy that is required to overcome and compensate for the loss, the aerodynamic losses in the slot at the acceleration point up to full duct velocity, plus 1 velocity pressure for acceleration loss. Don't forget that acceleration loss. Let's say it together right now at home. The acceleration loss is 1 VP. Acceleration loss is 1 VP. Remember that. Don't forget it. All right. On to the next. Let's try to simplify it. For simple hoods, our static pressure of our hood is just that loss here with the factor, the aerodynamic loss factor for the hood times the velocity pressure of the hood, of the duct. And it's right there where the duct and the hood intersect. Plus 1 VP of the duct. What's that for? See, you forgot already. No, you didn't. We know the 1 VP is purple. That's acceleration loss. Or our absolute value is this factor plus this factor. Just that easy. And this is what we're going to be dealing with in everything but compound hoods. This is what you'll deal with paint spray booths or laboratory exhaust hoods. This is what you'll be dealing with. Now, for compound hoods, we're going to have that slot. So remember, we're going to have a loss for that slot. If you will promise me that you keep your velocity pressure, your velocity at the slot less than 2,000 or approximately 2,000 feet per minute, I told you that that's what I wanted you to do. 2,000 feet per minute is your velocity at the slot. That times the loss factor will give you under 1/2 inch of static pressure. because the velocity pressure at 1,000 feet per minute is 0.25, and our factor for the loss factor for the aerodynamic for a compound hood is 1.78. 1.78 times 0.25 is less than a half. So it doesn't cause your slotted hoods to be much greater as far as resistance as one that does not have a slotted hood, which would be our aerodynamic loss factor for the hood times our velocity pressure of our duct. Always remember, what's the 1 VP for? Say it together, acceleration. There we go. In this case, our velocity pressure equals that greater value of either the velocity pressure of the slot or the velocity pressure of the duct. It's wherever the velocity pressure is greater. And in my lifetime, I have had one time of doing 35 years of design where the velocity pressure was greater at the slot than it was at another place. It's highly unlikely that you'll ever have to do that. And as a matter of fact, if you see that, it's something is probably wrong. Call me on the phone or send me an email. So here's another way to think about it. Our duct entry to duct loss, our hood entry to duct loss, which is right there at the corner where the transition is going up to the duct size. It's our aerodynamic factor of the hood times the velocity pressure of the duct plus acceleration loss 1 VP of the duct. That gives us our hood static pressure. That's for our simple hood. Note that the static pressure of the hood is a negative value by definition, but the absolute value is always a positive value, and you can think about it either way. I don't care. All right. What is the effect of the hood geometry? All right. What we say is that the most aerodynamic hood design is what's the most aerodynamic design in the universe that we know of? And I bet somebody's thinking a teardrop, and you're right. Or an egg shape. An egg shape is highly efficient in design aerodynamically. That said, why are eggs designed in an egg shape? Because chickens do not like to lay square eggs. It's a painful experience, but you're going to remember that. So that's our most aerodynamic, is a teardrop. When a teardrop translated into a hood entry is going to be a teardrop shape on either side of the hood, and it's going to end up being something like this. You've seen this shape before. It's a bell mouth entry. Where have you seen it? You've seen it on a trumpet, because it is the most efficient design for a trumpet. You've seen it on the inlet to a fan, a centrifugal fan. We'll show that tomorrow. At a later time. It's also, if we look here, this is the shape of a ball right here, or a teardrop here in the backside. And it's this is the most efficient design and the most efficient entry that aerodynamically you can do. And the losses are almost insignificant, 0.04 times the velocity pressure. So if we had a hood and we wanted to get velocity up to 4,005 feet per minute, which is 1 inch of water column velocity pressure, we would have our acceleration loss plus our F sub h is going to be would be 1.04 times the velocity pressure. Well, 1.04 times a velocity pressure of 1 is 1.4 inches of water column static pressure. That's telling you that we could, if we came back on a bell mouth inlet and we drilled a hole at 2 duct diameters back here, and we stuck a manometer on it and we measured 1.04 inches of water column, that would tell you that a velocity of 4,005 feet per minute is occurring inside this duct. How about that? It's just that translatable. Next, most efficient design is going to be one of these. They're going to be from 0.04, we'll jump up to 0.15, 0.2. Then the next one will be something like a transition that's a squared around, that's like that. That's going to be something that's about 0.25 times the velocity pressure. Or a flange. A flange will be about 0.06. And a plain duct end, just a sharp edge at duct end, 0.93. And then slots. Slots would come over here. We'd come over here to the slot, and that slot ends up being a sharp-edged orifice, also known as a slot. It must have sharp edges, must have very sharp edges. It is the most highly resistant design in industrial ventilation. It has a loss of 1.78 times the velocity pressure. But if you want, why would we ever have something that we wanted to be unaerodynamic or not aerodynamic? How about if you want to stop a plane and it hits on the ground? You want to stop it. What do? You take your sharp edge on the backside of the plane wing and you turn it perpendicular to flow. It'll stop it in a heartbeat. It'll bring it down. Well, it may not stop it, but it'll bring it down to 20 miles an hour real quick. And so these sharp edge orifices, or what if we want to use, we want a lot of resistance. For example, a paddle in a canoe. If you paddle in a canoe and you use a teardrop pole, how fast are you going to go paddling your canoe? You're not going to get anywhere. What you need is a paddle that's flat and has sharp edges on it. And the sharper the edges, the more resistance you'll have. So that's how it works, the same way in our industrial ventilation design. Acceleration loss is the transfer of potential energy to an equivalent amount of kinetic energy as the air accelerates into the hood. It always, from a dead stop, requires one velocity pressure up to whatever velocity pressure that is. What's the velocity pressure at 4,005 feet per minute? 1 inch of water column. How much energy does it take at a hood to bring it up to 4,005 feet per minute? 1 inch of water column. So it's just that easy. And it's always, if you only want to bring it up to 2,000 feet per minute, 0.25 inches of water column, and you will get 2,000 feet per minute with that acceleration loss. All right. Let's do an exercise real quick. A hood is designed with a hood entry to duct loss factor of 1.25. The hood is connected to a duct where the velocity pressure is 1.05 inches of water column. So that 1 point, what is the, we know the velocity pressure at 1.0 is a velocity of 4,005 feet per minute. How much do you think, let's use our knee jerk, what do you think 1.5 inches of water column of VP is? It's just a little bit more than 4,005, maybe 4,010, maybe 4,020, something like that. So the hood is designed with a hood entry to duct loss factor 1.25. What's the hood static pressure, SP sub H, for that hood? Well, we take our SP sub H and we take in this case, remember, we do not have a slot. So we take our entry, we have our F sub H. We're going to replace that with 1.25 times our VP of the duct. Our VP of the duct is 1.05 plus 1 times the VP of the duct, which is 1.05. So it's 1.25 times 1.05 times 1 times 1.05 minus 2.4 inches of water column. So if you come back behind this hood and you measure 2.4 inches of water column, you know you have a velocity in there, or a velocity pressure of 1.05, which is about 4,010, 4,020 feet per minute. Capture velocity. This is a sad one. This is one that Greg and I get on our high horse about. If you are at home measuring the capture velocity using a hot wire anemometer, then we dare you, Greg and I will dare you, and Greg, if I'm not right, please jump in and get me right. We will dare you to find the source that will tell you how to measure the capture velocity at X distance away from the front of it. Face velocities, yes, but a capture velocity out at 12 inches in front of the duct, there is no ANSI ATM, the ventilation manual doesn't recommend it. But what this is, when we talk about capture velocity, it's an important theoretical thing. We call it V sub X, and that is the velocity at X distance away from the front of the hood. And the actual definition is the minimum hood-induced air velocity necessary to capture and convey the contaminant into the hood. It is a theoretical number, but it is done by iterative testing, and it's based on a lot of years of it working very well. And in chapter 6, the chapter on hoods, it talks about this. And this is very important to remember. You tab this in your book. We talk first about the energy of dispersion. At what momentum is the contaminant being generated? Is it with little motion? Is it with average motion? Is it with high or very high motion? And what are we talking about? With little motion, that's evaporation from tanks or degreasing. Average motion is, are you pouring stuff into a container? Is it a low-speed container and conveyor and being thrown off the end of the conveyor? Transfers, is it welding or plating or pickling? And look at what we have, which we have corresponding out here for evaporation from tanks. We can use velocity, our V sub x, our capture velocity be 75 to 100 feet a minute. Note that it's going up as our average motion increases. It's 100 to 200 feet per minute for those last ones that we talked about. For high energy of dispersion, barrel filling, conveyor loading, high-speed conveyors, crushers, 200 to 500 feet per minute, because we're going to have to turn those particles around because they will have a certain amount of momentum. Very high, grinding, abrasive blasting, tumbling, 500 to even 2,000 feet per minute. All right, what is it? 500 to 2,000? Give me a break here. You know, this is, or 75 to 100. You give me 100, that's twice as much. This is more than twice as much. What am I talking about? How do I know? Strength, here's factors affecting cross strength within ranges. This is really good. The strength of the cross draft due to makeup error or traffic. Is this an area? Are they going to be using fans, cooling fans on them? Is there walking traffic? You saw what somebody walking by that hood did to it. We needed to jump that capture velocity up where that guy was walking by the front of the hood, if that's going to be something that's going to be happening periodically. Also, who would have thought of this? The toxicity of the contaminants produced by the source. Is it methyl ethyl death, or is it not just a non-hazardous, something like a non-silicate rock, or non-crystalline silicate rock? How about that? Something like limestone dust. Very different between those two. And the other one, exposures from other sources that reduce acceptable exposure from this source. The quantity of air contaminants generated, production rate, the volatility of it, how much is coming off, time generated, how is this done, how many times is this done per day? Is it done all the time? How much time does the employee spend at that station? These are very important parts. Hood issues. Remember, I told you, when you suck in air, you're sucking as good from your earlobe as you are out here at equal distance or close to it. Static pressure degrades in all directions, so its air is going to come in a sphere of influence all around your face and comes and enters. When we put a flange on it, we keep the air from coming from behind, and that keeps 50% of the air from coming in. And what that does is, because it's an XYZ kind of plane, it reduces the amount of air, because this is our formula. Q is equal to the capture velocity times the product of 10 times the distance away from the point squared. That distance is X. That's that distance away that the contaminant is being generated, plus the area of the face of the hood. That said, putting a flange on it reduces it by 25%. And know that the effective flanges, the width of this flange should, in order for it to be effective on contaminant reduction, it must be the square root of the area of the face of the hood. Flow rate is as a function of capture distance. There we go. At twice the distance, how much? We already know this. We need 1,000 CFM needed at X distance away. What happens when we do double the distance? We need 4 times the amount of CFM. How does this affect the horsepower? What do you think? What's the difference between capturing 1,000 CFM versus 4,000? Well, it's 4 times the amount of horsepower. Here's a formula that you might want to think about or mark, that the power is a function of volume times pressure. This is a number that is given to us by the Department of Energy. The fan efficiency is the fan efficiency. You can't change that for the application. So basically cover over the bottom of it. And so power is volume times pressure. And that's how that's, and we'll be talking about that later on. Here you go. And that's another way you see it done. Q, because that's volumetric flow rate, times pressure is P. 6343 is from Department of Energy, and the fan efficiency is written as new. All right, in the field, the single greatest cause of a hood not working effectively is disturbing air currents, machinery motion, grinding wheel in motion, material motion, the bag dumping. Somebody's dumping that bag and then they flap the bag around and they throw it up in the air. Those are other work practices. Work practices are huge. And what is the most important? Room air currents, personnel fans. This guy, this is probably this is a guy, and Greg, this is one of his pictures, but it's the perfect thing. He has probably got his exposure reduced to an acceptable level every time he does this. But the guy next to him is going to get a snoot full, I promise you. Personnel fans, the backside of a personnel fan is these personnel fans have velocities in excess, every one of them in excess of 2,000 feet per minute. They can have a velocity at 200 feet per minute to 250 feet per minute at 30 times the width. So it's a 3-foot fan. That's almost 100 feet away. So air projected in motion stays in motion and blows the contaminant everywhere. That's the thing that is so important. Go ahead, Greg.
Yeah, John, that was a leaded brass foundry, and their lead exposures were 6 times the PEL at that site.
I would love to have seen what their background levels were up in the rafters. You know, I bet they were just as bad.
There were a number of issues in that plant, so.
It's a great picture. All right, how do we measure flow at the hood? This is something that we talk about for you people that are studying for the exam, for the CIH exam. The 2 ways to do it. You can measure the flow in the duct connected to a hood, which requires a duct traverse using a pitot tube, or you can determine the hood's coefficient of entry, C sub E, which we will discuss in another module. But you're going to have to learn it for the CIH exam. It is, in my opinion, the most useful tool for someone that is doing repetitive quantitative analysis of hood velocities and volumetric flow rates. The C sub E can determine the volumetric flow rate with one static pressure measurement after a thorough inspection and quantification of the hood's volumetric flow rate is done one time. Once you do it once, you can come back, take a static pressure measurement, and you'll know what the CFM is from then on. And you can train your technicians to do it. And if you have more than 20 hoods that are the same alike, if you don't use the C sub E, then you are just doing yourself such a disservice. I can't tell you. All right, summary. Better enclosed is better captured. The secret to air distribution, slots. Remember, the slot loss has to be, the plenum loss must be insignificant compared to the slot loss, but the slot velocity is twice that of the plenum velocity. That's the secret. Air requires one velocity to move from a dead stop. For a plain hood, it takes 4 times the air to pull twice the distance. Static pressure of the hood, we know that. It's that the the factor times of the slot times the velocity pressure of the slot, the aerodynamic factor of the hood times the velocity pressure of the duct, plus one velocity pressure plus the other losses. That's simple. And you can blow air 30 times farther than you can exhaust it. There you go. And I tell you what, with that, we are going to have to cut. But Greg will be back to discuss the component parts and summing system losses. And just go ahead and open that one up, and you can continue on. Thank you very much for listening. Take care. We'll talk to you here later.